stop the recording for the. Okay. Yeah, no, we are doing this intermediate, I guess, a transition period thing where I am still on Zoom because you guys are all on Zoom. The rest of the committee is on Zoom, but the students are in that room with actual goodies to eat and everything. So I'm sort of sacrificing my eatables to.
Oh man, we're getting cheated.
I know exactly. So anyway, yeah. So I think Sachin is going to do his PhD comprehensive and proposal, and so I think we have an option. Normally, I ask the committee if they're okay with having the proposal be presented, and then have the questions on the comprehensive and the proposal be after that. If anybody would prefer that comprehensive be done earlier, then we'll have to do that. So any comments on that? Anyone? Okay, fine. So we will go with, then I guess we'll go with Sachin actually starting his proposal presentation. You have it for how much time approximately?
Around 50 to 55 minutes.
55 minutes. Okay. So he's going to be talking about his proposed research on human-aware AI methods for active teaming. And the committee is myself, Dave Smith, Siddharth Srivastava, and Kurt Van Len. Take it away, Sachin.
Hi, everyone. So first of all, thank you for coming to my proposal talk. As Dr. Rao introduced, my work is human-aware AI methods for active teaming. And my committee is Dr. Subbarao Kamampati, Dr. David Smith, Dr. Siddharth Srivastava, and Dr. Kurt Van Leen. So as the idea suggests, active teaming, what active teaming means is that these are the environments where humans are already working and robot wants to be a part of it. That would mean these are the scenarios such as in hospitals. There has been some research where they have been incorporated in for manufacturing cars as well. But there is a realization of, initial research has shown that there is a need to model the active human teammate. Another environment where robots are actually active participants with the humans are classrooms. In these classrooms, there has been some work where robots will interact with the students, and they will ask them questions or give them feedbacks and help them practice, interact with them. However, these systems actually run into a lot of personalization issues, where what to exactly present to the student becomes a difficult task. Before I go any further, I would actually set it up with a little bit of a background that would be needed to help understand the work that I have done. So I'll begin with the first one, which is automated planning. Automated planning is that there is a robot or an automated system in the environment, and its task is to figure out what actions it should take so that it can go from the start to the goal state. Finding this plan is what exactly the task is, and it's usually a search problem. However, when it becomes human-aware AI, at that time, with this robot, there is a human in the environment. Now, if there is a human, they might have some understanding of the robot's what capabilities, basically what the robot can do, what it is there for, and stuff of that sort. If a robot starts modeling this human's understanding of the robot, then they can actually use it to explain their own decisions as well as act explicably in the environment. Recently, there has been some work where human-aware AI systems have modeled these scenarios, and there have been some work where these techniques have been applied to explain. I will actually talk about them. The essential part is that human is an observer in this situation. How it will change, I'll talk to you in a little bit. When the human is an observer, robot can actually provide explanations. The explanations are basically, if I have explanations are basically the robot is trying to explain why it chose a specific set of actions. And what it usually is that it tries to bring this MRH, which is the human's understanding, to a level where it can understand why those actions were chosen. For example, if we have to say, let's say with an automated car, it chose a particular route. Then to explain it to the human, the robot can actually say that it chose it because there was less traffic on this route. Whereas it in another way, the robot can actually act explicably as well. What explicability means is that robot ends up changing its own plan and makes sure that whatever the human understands, they will about the robot, they will be able to understand the plan from that model. It in terms, it actually takes a hit on its own cost and then provides that plan that it would be easier for the human to understand. What if I continue with the same example, what it would be that robot will actually take, or the automated car would actually take a longer route, or a route with a big route with more traffic, so that the human is not surprised. This kind of work was explored in this seminal work a few years ago. This is what sets the tone of human-aware AI. And now, if we move to what active participant actually means, what it means is that they are working. That means this human model is an active participant, and robot needs to understand. Where it had to model MRH, it also needs to model the human's understanding. This, once it starts modeling this human model, understanding the human model, it can assist as well as teach the human. This is where active participant changes from the observant human. This is a novel scenario that for human-aware AI. In many cases, what happens if there is a correct model that you provide to the robot, that is how it should behave in the environment, which could be any sort of an oracle model, then this reconciling these two models becomes that the robot is actually trying to correct the human model. These kind of tasks have been seen for modeling this MHR and understanding MHR has been used for teaching, assisting, and even making better human-robot teams. This is how I have actually placed my work as well, where first I try to understand that can we reason with this this model that I say, and can it be used effectively for human-robot teammates, where specifically applying it to scenarios like such as intelligent tutoring system and decision support. Finally, I actually see that whether human-robot this model can be actually be reconciled to the true model using some sort of an interaction between the human and robot. So where robot can ask questions and whatever human responds, can it work? This is how I have paced my work over the years. This has led to some publications, few of which I will be actually talking about in this proposal as part of my proposal. To give an overview, first I'll talk about how automated planning and human-aware AI techniques can be used for modeling the classroom and can be applied to intelligent tutoring system. Then I will actually extend it to decision support, where the robot would be assisting the user. I will use this specifically to create a kind of user study to evaluate these techniques, evaluate the effectiveness of these techniques. Then I will I'll change gears and actually go to some sort of a reconciliation through interaction, or rather not reconciliation, maybe understanding, improving the understanding, refining the robot's understanding of the human's model through Q&A based interaction. Finally, I'll present the work in progress, which is evaluating this Q&A system through a user study. So first, I'll go to automated planning, apply automated planning to intelligent tutoring system. Just to give a background, why intelligent tutoring system? First, I mean, my master's thesis was more oriented towards intelligent tutoring system under Dr. Van Lane. And I have always I mean, it has a very broad history of actually 50 years of work where they have tried to model how students learn, how students work, basically have an interaction to understand that human model. These systems have been applied to general classroom settings where they are used by the teachers to provide material to students. And then over the time, they have also applied a lot of AI techniques to track the student model, to understand or to provide them questions and etc. And they have evaluated through a lot of user studies. So that is why I chose ITS, so that I can see whether can this understanding of MHR, our understanding of MHR and MR separately, can this work in something that has already been doing it? So this is my first work where I actually apply it. This work was in collaboration with Tathagata and Dr. Rao. And the idea here was that we take the human, that MHR understanding, we construct it and see if some of these automated planning and human-aware AI techniques can be used. How we try to do it is we actually try to model the behavior of a tutoring system, that how it would react to certain situations from the student and whether it would be able to, these techniques can actually respond in the similar manner as the tutoring system. We then looked at how we can actually take it a little further and try to incorporate it to more recent challenges faced by MOOCs, such as where they have a very low iteration rate, low rate of completion for their courses. So we tried to, we didn't actually give a solution, but we tried to approach it with what we could do. I'll be talking about it in a little bit. Before I go there, I will actually give you an overview of all the techniques. A little bit, there are 5 techniques that I'll explain. These techniques have been used throughout this work. So I'll just explain them. Plan generation. First is plan generation. As explained earlier, plan generation was that the task of the robot or the automated planner or the automated system was to take to figure out the action sequence that it needs to take, such that the environment, I mean, it goes from start state to the goal state. Well, the second technique that is the plan validation. In this case, what automated system does is it actually evaluates each action from the that has been executed and tries to check whether first that whether this action is applicable in the state in which it has been applied, and secondly, it would check whether after the sequence of all the actions, whether it could reach the goal state. In case there is something that has gone wrong, which it thinks it would that would not execute that action, then it would present with the cause and the action and the cause why this action cannot be executed. Going to third technique. Third technique is landmark generation. What a landmark generation does is that if there are multiple plans that can be executed to go from the start state to the goal state, and in case there is a scenario where some state, for now just understand this as state, although we use it a little differently, I'll explain. Some state has to be true, then that state becomes the landmark state for that plan, for the set of plans. This actually can be some condition that has to be true, or some like, for example, if I have an automated car, I have to go from point A to point B, but there is a point C that has to be visited wherever I go from, then that point C becomes the landmark for this case. But it could just be that it could not be the complete state. It could be some constraint that has to be true, or it could even be actions. So going to situation, I mean, technique, the fourth technique, which was plan recognition. Plan recognition states that if there are a sequence of actions that can be taken from start state to the goal state, and there are some actions that the user has already taken, then in that case, the system should be able to recognize what exactly is the user trying to do. Just for example, that if the observed actions are AI dash and AN dash, then the system should be able to recognize that this is the plan that the user is trying to execute. Finally, I come to the human-aware AI technique that I have utilized, although the models are a little different, but I'm taking the picture directly from the paper below. Here, what happens is, as I explained, this was this problem, the robot or the automated system is actually trying to explain why it chose a set of actions. What these explanation becomes are, these explanations are model changes that happen in the actual understanding of the human. And this MCE is called minimally complete explanation, which becomes that after this, whatever extra explanations I give, it would still stand true. So minimally complete is basically which minimal changes that are needed. And this becomes a sort of a model space search problem, where at every step, every subset of changes that might be possible, the system checks whether the robot's plan is optimal or not. Now, taking this over to a classroom setting, first I'll define what a classroom is. A classroom usually consists of some knowledge concepts that have to be taught to the student. These knowledge concepts can come from any of the courses, and it can be defined through any of the, for any of the material. The second thing is the tutoring material. This tutoring material represents how the teacher is teacher or some sort of a material that how these concepts are being taught. This could be video lectures. This could be a lot of the in classroom lectures by the teacher. Third is the assignments. Assignments are basically the student practices them from to learn those knowledge concepts. And finally, the student model, which is equivalent to the human model. We applied it to a tutoring system, Dragoon. This is the interface of Dragoon. Dragoon is actually used to teach students how to construct dynamic models. These dynamic models are basically, if I have to give you an example, that if a student is trying to model how the population changes, this is sort of the problem. This is actually the problem that is being shown on the screen, where there is a population that has been there, but there is some change that happens every year. And how would it grow over the year? This, in this case, it is trying to model the moose population, which is 20 at the beginning of 1900. And then every year, there are only births, and each moose has a chance of giving birth of 20%. So a student actually starts defining all the quantities, these variables like moose population, moose births. Moose births is nothing but population multiplied by the chance of moose giving birth. And finally, once it has completed all these quantities, it can look at the graph, how it is changing over time. Like here, it is being modeled for 20 years, starting from 20 and going up to over 600 in next 20 years. Similarly, other changing quantities, other quantities that change are also being shown in the graph. We try to model this. And what we ended up doing, we first constructed the model for this ITS. There, again, as I was explaining, there are two different models, MR and MHR, where MR consists of all the actions that a student can take on Dragoon. And MHR tracks the knowledge of the student. What it is doing is basically a combination of these two models is used to actually completely understand what exactly is happening in the environment. And the domain models were basically constructed by using the expert knowledge. We applied it to 3 different techniques. First was tips and hints. Tips and hints is basically what kind of feedback and stuff we can give to the student. There are 3 different techniques that we applied there: validate, recognize, and summarize, which are similar to what I was explaining a little bit earlier. Then we used on-demand curriculum. I'll explain it a little later. And then we used it for jigsaw problem. First, we go to validate. Validate is basically, this is how it would look in one of our automated planners, how the systems, how the plan is. It would be, there are 3 different quantities. I mean, first the student is constructing those create node actions are there. Then there are actions for actually filling each of the properties. And then finally, it has the student has applied his knowledge on this, completing this exponential growth schema. Now, in case the feedback is that supposedly student only executes 18 steps, then our system is able to tell it what exact changes that a student needs to do to understand, to actually complete this problem. This in this case, it hasn't completed this moose population node, and as well as the moose births quantity. And this kind of behavior was also part of Dragoon, and this is how it shows that not all nodes have been completed. For example, moose population has an empty expression, and this is what it is trying to explain here as well. So this is where what validation would mean. Next comes how we can use it for plan recognition. Again, plan recognition was that, if you remember, that there is a system which actually tries to recognize what a student is doing. In the ITS literature, it has been explained that it is essential that student is given feedback on what it is doing rather than what a system might assume is correct. With that idea in place, here, if you can look, there are actually 2 ways a student can actually complete the problem. And based on the actions that it has executed, the system is able to realize what exact thing that it is trying to do. That is, it is basically trying to go with the death probability first, and after that, it will define the birth probability, as both were needed to complete the problem here. Next comes the plan summarization. Plan summarization comes from the landmark idea, where if the system could figure out what are the essential parts that a student needs to complete, then that could actually act as summaries for the student. So what we did was we actually gave it another assignment that was there to the system, and it found essentially found 34 predicates that were essential that a student needed to complete. This was probably because there was only actually one plan that could have completed the system. But these predicates were somewhat like whether the moose population node has been completed, moose death probability has been completed, and so on. Quite a bit of, I mean, all 5 of them. Now we come to more recent, I mean, since all these techniques were already actually part of Dragoon. Now we come to something that we applied. Landmarks was actually not, but not to go there. I wanted to apply it to what exactly I bring to the table extra. So we applied it for on-demand curriculum. What was it? That we knew that MOOCs tend to have a lot of people, that students that join the courses, they don't usually complete it. And what ends up happening is that a student is, when it comes, if it knows the kind of assignment or the material that it needs to learn or practice, then it can ask our system what exactly they need. And given the current state, our system can actually find the explanation, the best possible explanation why they cannot do the complete the assignment right now, and what are the topics that they would need to complete it. For example, in this case, we are actually finding that the student 1 needs to complete these three knowledge concepts, understand these three knowledge concepts to complete the assignment. And since this is being done, it took some time to actually find it, because this was model space search. Going to the next problem, jigsaw problem. Jigsaw problem falls under the bigger umbrella of classroom orchestration. Classroom orchestration is that a teacher is actually trying to orchestrate a class, and it is ensuring that the student that is struggling can get appropriate help. But usually we all know that it happens that it is usually difficult for a teacher to support everyone. Then at that time, what the idea was that if a teacher can actually create some sort of a dynamic groups that can help, where the students can help each other, that can take the load off of teacher. So we took this problem, and we thought we could actually implement it. And we sort of implemented it and found that for a given tutoring assignment for Dragoon, we could actually, for a two student groups, we can actually, if the student 2 was the sharpest student, we can provide them, they can learn the tutorial, and then they can actually help student 1 understand the material as well. We extended it and applied it to up to a 20 student classroom for Dragoon assignment that we were trying to do. There were 7 knowledge concepts, 9 assignments, and we compared the number of actions that in which the students can complete these tasks, and we found that overall there was a decrease, because now with groups, students can teach each other, and the unit can finish faster. Finally, we also wanted to actually test if it could do such a apply such a technique to different kind of classrooms that might exist. Like what we fixed was there were 20 students in each class, and there were 10 knowledge concepts that they were trying to practice. And any assignment can be done with up to four different knowledge concepts. In that case, we found that overall it led to the plans that our system created were actually faster by 3 to 7 steps for completing the groups, for completing the class unit. And but however, faster completion might not be the metric, and different kind of metrics, we believe different kind of metrics can be incorporated to judge how groups behaved while working in the class. So the key takeaway for this work was that we were able to, for the first time, we were able to show that these automated planning and human-aware AI techniques can be applied to something to model the human and define it as MHR. And we applied these techniques to a real-world tutoring system, which was Dragoon. It has been applied to many classes in Arizona State University. And we took it a step further to actually see if some other real newer challenges can be handled with it. Well, we applied it to MOOCs, basically. But this doesn't mean there is a complete evaluation, right? I mean, it's just showing theoretically it can be applied, doesn't mean that it might be useful in the real world scenario. So what we ended up doing, we created a decision support setting where human is trying to construct a plan for their own requirement. Human is the stakeholder, and they are trying to they are interacting with the planner, who is actually ensuring that the rules of the domain are actually followed. This sort of can be a generalization for something what a student might be doing as well, and they're solving a problem. The system can ensure that all the knowledge concepts and everything are understood and actually correctly applied by the student. So the whole idea was to actually to see the effectiveness of these techniques for real world problems. And this work was presented in was accepted at a journal, in a journal, HCI journal, and it was presented at multiple conferences, and it was very well received over 2 years. So this another point that actually I'd like you guys to note, that since we have been able to apply it to multiple such settings where a robot is able to support, this actually shows that these techniques that we are talking about are domain independent. And if we model the system correctly, we might be able to harness it. And these techniques can be separated from the actual tracking of the humans model. For we apply what this decision support setting was for our user study was that we asked students to construct their plan of study. Plan of study is something that we have constructed for our degrees as well, where what are the courses we will be taking, and we provide these kind of details to our advisors. The rules that we defined were something on that line, where we said that for a student to graduate, the goal was to graduate, the student needs to complete 30 credits. There might be some deficiency courses that you might know from the computer science department. There has to be an area of specialization. They should be taking research courses. They should be completing research specialization courses. And the defense has to be scheduled in the last semester. With this idea in place, we constructed a new model, where first model was MR, where the robot model consisted of how the student can interact with the interface. I'll talk about the interface next, but just to distinguish, and MHR was the students' knowledge of the domains. Basically, they were the rules that the student might understand. Since we were trying to use this system for providing support to human, what we did was we assumed that this model was completely empty and human didn't understand. In cases, what would have happened, the robot actually might end up explaining more than it is needed. But even then, it would essentially ensure that all the rules that are required are actually properly followed. This we constructed these models, and basically we evaluated the effectiveness through the user study. This was the interface that we had built. This interface was actually divided into 3 panels. The panel on the left was giving the student information, which is whether the student is an international student or not, whether they are an RATA, or whether there are deficiencies that are already completed. And we actually incorporated all 6 deficiencies. So in this case, these 3 are not available, but the other 3 might be. The middle panel was were the actions that a human user can take on the interface. These combined to form the robots model. So these actions were choose the course, choose the specialization, choose the committee, use the defense courses, and schedule the defense courses and stuff. This also had this check button. I'll talk about these buttons a little later after this. On the right side was the interactive plan of study that student had already created. This was this tracked how much time the student had spent, as well as what exactly were the functionalities that they had: validate, suggest, and explain. Again, I'll talk about these functionalities in a little bit. And it also showed the plan of study that the student had already constructed. First, I'll walk you through those user-facing functionalities, which first was plan checking. Plan checking was that given a plan that the student had constructed, it would click the check button, and it would show this would check whether the plan that the student had constructed would lead to their graduation or not. In this case, since they only had one action, the system was told, system would tell that this hypothesis is not valid. However, it would not give any feedback as to what was wrong with it. First, thus the second functionality that we had was it was validated. This would actually lead to, this was similar to what I was talking about earlier, which was plan validation. And it would give a response step, it would check step by step whether a student is actually, can the plan action the student has chosen can be executed in the state or not. So in this case, since there was, the student must finish the deficiency courses before, that this kind of response was, specific feedback was actually suggested to the user. Next is suggest and explain. Suggest was that if there is a plan that the student has constructed, then the system tries to complete it. It actually goes through 2 steps where it is plan recognition, and then it would realize, okay, once it has recognized, what is that plan that the student is trying to execute. And we ended up, and it would present that plan to the user. After this, there would be a button here which would ask for, where the student can ask for explanation as to why these actions were added. And this would lead, this would show explanations in this form, where adding normal course requires completing the deficiency courses. So basically this was the normal course, and these were all the deficiencies that were added before. This was the problem that was sort of, functionalities that the users were provided. In this case, we evaluated the study. Since we wanted to evaluate the effectiveness of these functionalities, we constructed the study around these, and there were 4 conditions that were there. First was control, where only plan checking was available. None of the validate and suggest and explain was available. First, then was condition C1, which was plan validation was provided to the users. Then there was C2, where plan suggestion and explanation was provided to the user. And C3 was where all these facilities were available to them. The user study was run, and it was run on 56 students across these 4 conditions. There were 13 to 15 students in each case. Out of these 56 students, 18 had already constructed their iPods. And the whole study was executed in this manner, where they were asked to create first iPods. Then there was a feedback form, and then they were asked to construct another iPods for a different initial state, and then they were given the feedback form for the second. So basically, there were 2 iterations of these iPods. The hypothesis that we had actually had 3 hypotheses. These are the 3 parts of the first hypothesis, where the first hypothesis was that with more feedback, the student it would be easier for the student to construct these plan of study. Or more feedback or more support from the system, it would be easier for them to construct the study, and they would also be more satisfied. The second condition was that we believed that the second time when they construct the plan, it would take lesser time for them, and with more feedback, it would take even lesser time. Basically, the second time, if a student is working on condition 3, using condition 3, it would have, since it would have got more interaction with the interface, it would understand the rules of the domain, and thus it would perform better. And H3 was that the student, which were non-expert, for example, in this case would be that students who have not actually constructed their iPods and they don't know about it, the feedback of the system would help them more. For all these conditions, we assume that the more the feedback, more the interaction, thus it should actually perform better with the help more for the students, provide more help for the students. So I'll quickly walk you through the results now. In this case, I have on left axis, on the vertical axis, I have the 2 iterations, and on the right axis, I have the time taken by the students. We found that for the first iteration, control, only condition 3 had statistically significant improvement over control. Whereas there wasn't any significant improvement for condition 1, 2, and 3. However, but if for the second iteration, it was shown that even C1 and C2 had statistically significant improvement compared to control. But there was again no comparative result between the two. For satisfaction, we actually asked users to whether they were satisfied with the IPOS that they constructed. We actually asked them 2 questions, and both of them had very similar results. So I'll just walk you through with hypothesis 1B. We asked them on Likert scale whether they found they were satisfied with the IPOS that they constructed. And we found that the average score did improve over them, but only statistically significant improvement was seen while comparing control and condition 3. For hypothesis 2, where we evaluate the time difference, we found that only C3 as compared to control and C1 as compared to control had statistically significant results, but nothing could be said between the 3. And these systems, our idea was that our belief was that giving step-by-step evaluation actually helped more, was more helpful to the students. Going with for hypothesis 3, where in comparison to non-expert users, there were 18 students who had some experience for IPOS, and we didn't see any significant, statistically significant result in differences between the two in any condition. And basically, this was primarily because there were not a lot of students with experience across the conditions. So just to give you a summary of where these were the expected results, like for example, the time taken would be more for control as compared to condition 3. We found that the only outcome was which had improved was shown improvement was for condition 3, and rest were all similar. Similarly for the satisfaction, however, satisfaction with the interface actually had NC1. Number of people who actually liked the feedback was more, and similarly for hypothesis 2 and hypothesis for hypothesis 2, they actually there was a only improvement between condition 3 as compared to condition control. Rest were all null hypotheses in both H2 and H3. So with this, we could actually show that what we imagined, that how we would apply these techniques, they can be actually applied to the real world scenario. We were able to do it in the real time, and all those technical issues that might come about while working with the students were actually handled. And we found that these techniques were effective to an extent that if we believe that if we had a more thorough study with more students, it might show even better results. And it's in human-aware AI technique. From those techniques point of view, it is one of the first study of its kind which actually evaluates whether these techniques are even effective or not to be deployed in real-world scenarios. Going to third part of my work, which is where I actually look at whether the system can interact with the human user, and with that interaction, it can actually evaluate whether it can bridge the gap between the two through a Q&A based interaction. This work was done in collaboration with Dr. Smith and Dr. Kamampati. And in this case, the essential idea is that the motivation is that these understanding this humans model and what they can do. If a robot knows this, then it would be easier for it to model what exactly is going on in the environment, and probably support or probably do any sort of extra facilitate the user in any way possible. These kind of does having a clearer understanding and having it closer to the human model can be helpful. Again, this is motivated from the ITS system, where tutoring system would ask questions to the students and understand whether whether a student understands the concept or not. From these systems, but there is one thing that we need to be careful about. Since we are actually planning to use this in real world scenario, where the robot shouldn't be overwhelming the user at all. There are some human factors, human factors effects that the robot need to take care of. Which would be like, again, the question shouldn't confuse the user, or it shouldn't be overburden the user, and whatever response a human give, the robot should be smart enough to understand what exactly, which part of the model or what exactly subset of models is this robot, is the human pointing. This should also include more specifically the negative responses, because it usually becomes hard when they say that when the human says that they cannot do it, and there could be multiple reasons as to why this failure is. It becomes hard for the robot to understand which model or what subset of the model is the human pointing. In this case, just to set it up as how it was set up, was that we assumed that the human robot, the robot's model actually had a set of models that were possible, and it assumed that this human model was actually part of it, that MHR consisted of this set of models. There is something called as diagnostic questioning, which comes with its, which has been tried, and something that gets used in a lot of tests, etc., is that the automated system should construct a question where the responses can actually help refine this hypothesis space, right? Ideally, the question should be where every response that the human can give would point to a single model. That would be the best case scenario, where whatever response that a robot gives, we know the corresponding model. But usually it might not be possible in the real world setting, where what would happen is the question could be too confusing for the human, too difficult to understand, or it could even be difficult to construct for the robot, where it is not able to separate, and same response can be part of multiple models. In that case, the robot should look at the best case. The next best step is to divide this hypothesis space into equal sets, where each response, the response R1 would define half of the models from this, and R2 would define half of the models. So taking basically this whole idea can be divided into two parts. First is understanding the hypothesis space that the robot has, as well as, and then apply it for the responses that the human can give. In this case, if I first start with understanding the hypothesis space, there could be there are two models that can exist in this hypothesis space. One is the constrained model. Constrained model says that all the rules of the domain that are actually constraining what can be executed in the environment, all of them are assumed to be true. Human understands them or doesn't understand them is a separate issue. But there could be a model where all of them are supposed to be true. This would mean that any task that we give to the human, if he understands all those constraints, basically it would be hardest for them to solve the task with that model. And then there is a relaxed model. All the constraints that are there are assumed to be false, and thus it is easiest to solve the task in the model. However, but how should robot go about it? So robot or the automated system can actually isolate each and every domain and ask specific questions to the user, directed questions to the user, where each response can help them understand whether a specific rule of the domain is understood by the human or not. In this case, what it would mean is that the robot actually ends up relaxing only one constraint and then asks a question where question is again from the initial and the goal state, and the response from the user will tell whether that particular constraint is part of the model or part of the true model or not. How, looking at what the responses can be, the easiest response for the human could be if we could construct such a simple question where whether can they go from this initial state to goal state, and if the responses are yes or no, then no would mean that the predicate is present. We want to construct a query in a way that the no response can tell us that, okay, it could only be because the constraint actually exists in the true model. And if they say yes, then it could be that it is basically absent in the true model. Now, what we have done is we have actually defined how for one constraint that is present, the robot is able to cut the hypothesis space by half. Second response that is possible is basically pi-h. Pi-h is the plan that they would construct for initial to goal state. In this case, what would happen if the cost of the pi-h is actually greater than the cost of the plan? In this case, that would mean that the plan is from this model and the predicate is actually present in the human model. And similarly, if the cost is less than that, then the predicate is absent in the true human model. To take this a step further, what if there are two constraints that a human that an agent is trying to ask for? Then it becomes a little trickier, because at that point, the robot needs to ensure that the question is such that it can, all of these plans exist. Because what would happen is if there is failure due to either of the constraints, then there would be two subsets of the model that would exist. And then it would again require two questions instead of one, which we have already discussed. So thus, to ensure there are no assignment of blame issues, the plan set should not be empty. Only then the robot can question about multiple unknown predicates. This led to actually three different types of queries, which I talk about in my work, which is the validation query, where the response is yes or no, the plan generation query, where the response is pi-h, and the template queries, where multiple constraints can be asked and there are specific conditions under which it can be asked, and which ensures that all the subset of the models will have some valid plan in each scenario. Going to just to give you an intuition of how these plans can be, how these queries can be constructed, is that we have to ensure that the question, the predicate, the constraint that we are actually asking about, that should be the landmark in all the plans that a human can construct. That would mean that the goal of the query becomes the add effects of the action. And similarly, the initial state is actually constructed by changing the initial state of the environment, so that this ensures that only subset of the predicates are true, which would ensure that only all the plans need to go from AP, and none of the other actions, special care is taken to ensure other plans cannot be executed. From this, we were able to construct a lot of queries, and we were able to do it for 4 to 10 unknown constraints. And although I talk about constraints, we had it for effects as well. And I randomly chose 4 to 10 unknown predicates in the model. And we were able to construct these queries in under 30 seconds, roughly under 30 seconds. Then we were able to ask questions. And for the easiest response, which was yes or no, only 50% of the scenarios we were able to construct those validate queries. In other cases, we needed some sort of a plan from the user. With for evaluation of the bigger model, what we did was we increased the number of objects that were there in the domain, and we did it for rover domain and with 6 unknown predicates, and we found that almost same amount of time was taken to construct these queries. Now we have basically shown that okay, theoretically it is possible that to ask that the robot can construct questions in a way where every response or a response from the user can be understood by the robot, and thus there could be some sort of a reconciliation that can happen between MHR and MH, and the robot can actually take MHR closer to what a human model is. Our evaluations also show that these interactions are possible in the and they can be useful. But what exactly now, what the work in progress that I have is that I'd like to evaluate these system through Q&A. I have created a scenario where the robot, this is a picture from our robotics lab, and there are 2 tables, and this the robot is in an environment where it is working, and the human can work as well. And robot is trying to understand whether human understands the rules that are with which the robot is running. These rules could be like that when a robot moves, that the robot's torso, which is this, should be in the should not be in the elongated form, otherwise it can topple. Then as shown, there are heavy blocks and lighter blocks and blocks. Sorry. So whether it can carry, in what cases it can carry, and whether another rule was that only lighter box can actually be transferred from one table to another, and stuff like that. These were the sort of the constraints that were constructed on which the human would be questioned on. I also constructed an interface where, again, I divided it into 3 separate panels. For the left panel, is for asking questions. Second panel is for showing them the plan or asking them to construct the plan. And third panel is actually for where a student enlists all the rules that were used that they think would be useful for them to solve this problem. I actually plan to complete this user study over next 2 months, and this is what the timeline for my study looks like. I mean, in next 2 months, I would like to finish it, and then I would do thesis writing in January and February, and probably have defense around second half of spring semester. Coming to the conclusion and future work. Conclusion is basically that I set out with a goal that I wanted to understand how I come from IT's background, and how human-aware AI techniques can be used to help or to what we can learn from those ITS systems to understand this MHR model. And then what are the ways to refine the second challenge was that how can I actually cause some sort of interaction with between the robot and the human, and how there can be refinement of the robot's understanding through interaction, because the roommate is there in the active environment. And then this basically, I believe that this can be the first step towards creating more human-aware systems where robot not just understands what human thinks of the robot, but they also understand what human capabilities are and what they would like to do. And from there, it can actually have a more active participation in the team's collaboration. Finally, I would like to, these are the publications that I have had, and that this concludes my presentation. Thank you. Any questions?
Okay, so so I guess can you go back to the conclusion slide?
Yeah, sure.
Okay. And also, I think we have a public session where both the committee members as well as anybody in attendance can ask questions, and then we will close the public session, and then only the committee members will ask questions. So right now, public session. I mean, committee members can ask questions anytime. You know, does anybody have questions that they want to go first?
Take a stab at a question.
Yeah.
For the proposed study, that's going to be done with real people, right?
Yes.
And what you're trying to do is figure out what the real person's plan is by asking questions.
Yeah. Model is. Yeah.
Where do these people have, how would they even have a plan? Do they know anything? And this is about robots, right? This is not.
What I have actually tried a few ways to explain all the rules that are there in the environment. And I tried to construct it in the initial, at the beginning of the year, where I had written the rules and I ran it through some students, but they were not able to understand what it means. So currently I'm creating some sort of a tutoring material, which would explain all these rules to them through some videos, and where they can understand, okay, a robot can only work like this. And from then on, the robot can ask, and then when I ask, robot can ask the question about specific rules in the environment. The human can answer, and from there we can understand whether the rules were clear to them or not.
So if you'll back up to the user interface, which has a list of rules,
Yes.
Those are the kind of rules that you're going to teach them, and
Yes.
then the robot's going to quiz them.
Yes.
So I don't get it. Isn't that normal? Like we teach them and then we quiz them? Like they can look at these, they'll say to themselves, torso should be contracted while moving. Did Sachin tell me that was true or false?
But in this case, this is actually happening in, we are evaluating through the questions that the way we have constructed questions, where we have assumed that there is a human model, and from there, the refinement process can begin. I mean, this is similar to how the questions may be asked from in practice system, but they are not usually constructing questions like this. From here on, since it is active environment, there are more constraints which are not present in those tutoring systems that might exist. Like, the robot doesn't want to ask questions which might confuse them. It is also taking an extra step that whatever the human might say, the robot is able to understand. There are some extra constraints that are actually placed in this construction, which are different from how it is done in the tutoring system scenario.
Okay, so what I'm understanding is, in addition to these rules that are printed here,
yeah,
there's some other rules that you haven't told them about. They weren't
yes.
instructed on.
Yes.
And you're going to try and find out whether or not they possess knowledge of one of those hidden rules.
No, actually, what I'm trying to do here is I'm actually trying to distinguish it from how it is done in ITS. Where in ITS, the student a teacher can ask as complicated a question and it doesn't really take into account all kinds of plans that a student might be able to construct. But since it is a robot and robot is trying to interact, it is taking extra care of constructing a question in the way where whatever response the student might give, the user might give, robot is able to understand that response. So it is going through that extra loop of while constructing these questions. This is what the idea here is, that whether robot in the working environment can ask questions and understand that whether they understand the rules of the environment that they are working in.
Yeah, I'm just trying to think about this from the standpoint of being a subject in the experiment.
Yeah.
It would feel to me like I've been taught some stuff about this robot, and now I'm being asked questions about the same robot. And it's going to feel to me like I'm being quizzed on my knowledge. And if there's some knowledge that I wasn't told that I'm being quizzed on, then that's going to feel kind of unfair to me. You didn't tell me that kind of thing. But on the other hand, all the other knowledge, I suppose, that I was told, if, you know, they're going to feel like there's a right answer and a wrong answer. So like whether the hand should be tucked in while moving, that's either going to be something that they were supposed to have learned or something they were not supposed to have learned. And so they're going to feel like this is quizzing them on their comprehension of the instruction they received.
I guess another way to pose that is, are you testing or attempting to test recall or inference?
I am actually attempting to understand that it is more related to inference, where recall, the rules are already there. So it is more about understanding whether these questions that are asked to pose to them, they can actually whether these rules are of working, since they are in the same working environment, whether these rules are actually understandable to them, how they apply, how they affect, how they would work, things of that nature. So it is more of inference rather than recall.
Well, I guess what I'm thinking is, since you're not, I mean, your ideal case would be that you bring in a bunch of firefighters who have already in their minds various plans for how to fight fires and stage engines and knock down doors and stuff.
Yeah.
And different fire chiefs have different plans. Okay.
Yeah.
And they really know what these plans are. They do them every time they fight a fire.
Yeah.
But you don't know what their plans are, and you would like to know whether Chief A has got the same plan as Chief B and what those plans are.
Yes.
Okay. So that would be your ideal set of subjects, but you don't unfortunately have those access to those guys.
Yes.
I think what you're trying to do is construct those guys. So if that's what you want to do, then I would suggest that you do train these people, but you train each person differently. Some people have one plan, some people have a different plan, and you train them up to criterion so they can, their recall is perfect, or well, 95%.
Okay.
Okay. So they are just like the fire chiefs. They really know this stuff, but the robot doesn't know what they know.
Okay. Okay.
Now you know what they know because you taught them.
Okay.
And so you're in a great position then, because then not only you can look at what the robot did, and you can look at what the people responded, and then the robot at the end of the day is going to say, I got it. I know what this person's plan is. And then you can look and say, oh, this is person 5. This should be the plan I taught them. Oh, look, robot thinks it's 5 prime. It's not exactly the same. So you'd be able to say whether or not the plan it inferred from the person's responses was correct vis-a-vis the plan that you taught that person. So correctness could be the dependent variable.
Okay. Okay. I actually was.
I'm curious whether you're going into a direction that you didn't intend to, which is, it seems to me that the point of this test, this study, was to see whether the way the robot phrases the questions are effective enough to learn the human model. Now we seem to be thinking a lot more about whether the humans have learned what they have been told. I mean, I'm wondering whether you seem to be sort of, I mean, you have to set up the experiment such that the humans have certain model in their mind, but really what you care about, isn't it, whether or not the questions that the robot poses to the humans will be effective in letting it acquire the human model.
Yeah, Dr. Rao, that is actually absolutely correct. What I feel Dr. Vannan is saying is change the initial state of what you might be teaching them so that you have some variance, and with those you can you can teach only each one of them a subset of the rule, randomly choose the rules, or maybe fix those rules, and then from there from those subset of rules, see whether that subset is actually understood by them, by these questions. And
again, what would be more important, it seems to me, is I like the idea of subsets, but it seems to me it's more about whether the robot was able to get that they actually understood that subset by the questions it asks. Because I'm not really sure where you got into checking whether the humans understood the instructions, because at least that's not, this is supposed to be the study for your acquiring models by questions.
Yes, and the point for the user study, the problem comes is that I need them to have something like I could do this for a subject where some subject that they have already been taught like calculus. But in that case, what would happen? It would be like a pretty vast area. So what I am doing is, for example, if I take firefighters, there would be a lot of rules that would be running around, that would be true in the actual environment. Now, in this case, what you are saying is also, I mean, it's exactly correct that we need to infer from the questions, the rules that might be true. And if I only actually teach them the subset of the rules, those models would still be part of the same hypothesis space, even if because they were not taught. And thus, I would still be able to figure out exactly the model. And basically, what would happen is the closeness, the closed world condition which we need would still hold. If I have worded this correctly.
So if I can be so bold as to propose,
Yeah.
suppose that you just work with the actions you've used in your examples, move, crouch, and tuck.
Yeah.
Okay. And there's the move action could have 1, 2, could have crouch, tuck, or both as a precondition.
Yeah.
And crouch might have tuck as a precondition.
Yes.
And tuck might have crouch as a precondition, and so forth. So there's a finite space of possible preconditions.
Yes.
And so each of those is, as I understand it, a model, one of your MIHs. Okay,
Yes.
so you teach, suppose there are 25 of these. Okay, so the fancy experiment would be to take 25 people, take each person and teach them one of these 25 models. And they're not hard models, right? It's just memorization, right? In fact, you can give them a cheat sheet. Who cares if it's in their head or on a piece of paper? It doesn't matter for your experiment. So they've got their cheat sheet. They've got their what they can remember from this. And now the robot asks them these questions. That would be, and then you know what model they were supposed to teach the robot.
Yeah.
And you know what model the robot came up with, so you can compare how far apart they are.
Yeah, I mean, cheat sheet part is actually already there because I had already considered this part. I don't want them to learn these rules. I would like to know whether they can apply these. So the cheat sheet is actually already here. All the rules that I was teaching them are already part of the interface where they are actually practicing, giving responses. So I hadn't really thought about choosing subset because I was trying to understand that how. Well, you're right. In that case, I'm more actually evaluating how well the teaching process was, and this might be useful. I will actually consider this and try to talk to you more about this soon.
Okay. Well, the other thing I'm curious about is, do you really need that list of rules over on the right in this user interface?
Yeah, at that time it was the idea was that I was cross-checking them whether because I knew from the question the robot knows what exactly rules are needed to be applied. And this was more of a cross-check whether these students actually thought about the plan and they knew what the rules were, if they were partially known to them, or what was exactly happening. So this was more also on that, does it even asking them plan of how to work in the environment, does it even reach the does even the student even understands how it is working. So that was more of like a sanity check with each question that I wanted to have. It was more like if they ticked all the rules but they didn't apply, that would mean that they sort of had an understanding but the question wasn't clear. And that sort of a cross checking what I was trying to do with these set of rules.
But what I guess what I'm thinking about is that list of questions. If the person ticked off the rules that they were using, and the robot saw those ticks, then that would be a big advantage for the robot in terms of figuring out what this person's plan model was. So is the robot going to have access to the person's ticks on this rule list?
In the real world scenario, that might not be the case, and because it is usually very hard to know. This can only be done in a control study that I'm creating, and I am sort of using it in the to actually cross verify. But this might not. This would give us some intuition as to when a robot poses such tasks to humans who are experts, then whether they really understand what the point of the problem was for the human and what exactly are they supposed to respond. And that would sort of give us some insight, at least for the user study. In the real world scenario, Dr. Allen, I don't think it is really possible to actually construct such list of rules that a student is supposed to follow. Firefighting in itself can be very big problem, and it could lead to a lot of contingencies and whatnot, and it takes a lot of time to construct such rules, basically.
Okay, thanks.
So Sachin, I have a question on the same setup before you move on. So in this, if I understand correctly, the setting is that the robot knows the true model of the environment, system, whatever it is, and you're trying to figure out what the human's approximation of that model is. Is that correct?
It is correct. We don't actually use it in our, we try to stay away from it, because if I wanted to continuously simplify this problem, it would rather become like if there was a global task that the human robot team was actually trying to do, then I would only need to ask, I can further infer down that, okay, I need only these subset of tasks. I try to stick to a problem where it would be just from that interaction, can I reconcile these models? And that is where my motivation originally comes from. So I try to, even if there is a correct model, I could, like a tutoring system could be that use that correct model and actually provide feedback to the student. It could further help, but it is not a teaching scenario. This was the whole idea, was just to reconciliation, sort of, if I make sense.
Right. So one of the interesting things that you mentioned was you want to find questions that are less confusing.
Yeah.
Do you have any ideas for how, what factors you might use?
For confusion, I was basically defining where I would have a very complicated question. Okay, go to table 1, do this, then go to table 2, then you have to do this. Where all
the
those
length of the
exactly. The length of the plan would continuously increase, and that would be, I would believe that would become more and more difficult for the user.
Thanks.
Any other public questions? Okay. If not, then I would suggest that the public, everybody other than the committee members get off the Zoom. I guess that includes the 210 room. And then we will have the private session. Okay. I think I have everybody still, right? Yeah. Okay. So now just Sachin and the committee are there. No, I should also stop the recording.